Hello again. This lecture is on framing curves. It's for Math 4250 at the University of Georgia, and I'm Professor Jason Cantarella. One of our uses for space curves is to compare the paths of objects moving through space. So we're going to compare this path for the turtle with a really different path. Now you'll notice that the turtle covers the same coordinates in XYZ space. But if we look at the pictures together, we can see that something is really different. The turtle on the right is spinning, while the turtle on the left isn't. We're now going to give the turtle a more complicated, computer-generated path. Here it is, swimming around in a little turtle box. We're drawing in the curve as it travels, so we can see the ground it covers. Now here's a different flight path for the turtle, which still covers the same curve in space. What we want to do is distinguish between these two paths. It seems clear that the second one is spinning, but what do we really mean by spinning? Spinning relative to what? To keep track of the orientation of the turtle, we'll now draw in a little ribbon coming from the turtle's back and remaining along the curve to show which direction the turtle was pointing at each point in the flight path. When we do this for the path where the turtle is rolling as it swims around in its loop, we see the ribbon looks really different, even though the path looks the same. This ribbon defines what we call a frame. A frame is a map from the parameter space R to 3x3 matrices, so that at each time the matrix is orthogonal. The matrix times its transpose is the identity matrix. The three columns of the frame matrix, the frame defines an orthonormal basis, A1, A2, A3, where the three vectors are given by the columns of the 3x3 matrix. Now in the past, our bases for R3 have been static, but this basis will change as t increases to maintain an orientation with respect to the curve. It's conventional for the first vector in the frame to be given by a scalar multiple of the tangent vector of the curve, but defining the other two is the interesting challenge. Here's what looks like a natural frame on the circle. The frame vector A2 just stays in the plane of the circle. We can define spinning with respect to this plane. We're just spinning from the plane of the circle into the z direction and back again into the same plane. The turtle is making a total of 15 complete revolutions as it travels around the circle. Our first circle frame, the flat one, looked particularly physically natural, and there's a reason for that. If alpha of s is a unit speed curve, we can define the acceleration frame, which is also called the Frenay frame, in the following way. The first vector, a1 of s, also called the tangent vector at s, is simply the derivative, alpha prime of s. It's a unit vector because alpha is a unit speed curve. The second vector is given by the second derivative, divided by its norm to make it a unit vector. That's called the normal. And the third vector, called the binormal, is simply the cross product of the first two. In fact, the TNB frame is orthonormal for every value of s. And that's what makes it a frame according to our definition earlier. This isn't so hard to prove. We already know that the curve is unit speed, and that means that the derivative of the norm of the curve is equal to 2 alpha prime dot alpha double prime is equal to 0. So that means that t and n are orthogonal. T and n are orthogonal to b because of the properties of the cross product. The cross product is perpendicular, remember, to both vectors that go into it. And of course, the lengths of all these vectors are 1. Now we're going to look at the Frenay frame for a helix as we increase the pitch angle of the helix. Notice that the frame stays more or less the same. In fact, the frame is always pointing directly towards the central axis of the helix, something we can see if we expand the frame until it reaches the axis, and then squash our family of helices back down again to a circle. Now we're going to compute the Frenay frame for a helix by writing down a parameterization. This one, cos s over root 2 sine s over root 2 comma s over root 2, is already arc length parameterized, as we'll see in a moment by differentiating. Alpha prime of s is minus 1 over root 2 sine s over root 2, 1 over root 2 cosine s over root 2, 1 over root 2. That'll be our vector t of s. To compute n of s, we start by computing alpha double prime of s. That's minus 1/2 cosine s over root 2 minus 1/2 sine s over root 2 comma 0. Now to compute the normal vector n of s, we have to find a unit vector pointing in the same direction as alpha double prime. It's not too hard to see that we ought to simply erase the 1/2 and get minus cos s over 2 comma minus sine s over 2 comma 0. This vector points in towards the axis of the helix at every point along the helix. To compute the binormal vector, we're simply going to take t cross n. That requires a little calculation, but I got 1 over root 2 sine s over root 2 minus 1 over root 2 cosine s over root 2, and I had to think about it for a moment, but it simplifies down to 1 over root 2. One thing I want you to notice about this formula is that the n of s formula tells you that there's no acceleration along the axis of the helix. We can see this as we watch the turtle traversing the helix. It's got a constant speed from left to right, even though it keeps accelerating in the direction towards the axis in order to change course. If this is a little disturbing to you, remember that if the turtle had no acceleration, it would have to travel in a straight line. We're now going to think about how frames change as you move along the curve. So here's a curve and a couple of tangent vectors, and I'm going to draw the normal vector in blue. As we move along the curve, the normal vector is changing, and its derivative is shown by the red arrow. We call this bending. This is where n prime is parallel to t of s. But let's consider another situation, which it'll take me a moment longer to draw. There's our curve, alpha of t. But now, let's imagine the frame vector moving around the curve rather than just bending with it. It's magic. Suddenly we see the normal vector in blue and its derivative in red, and we see that in this kind of motion, n prime is parallel to the binormal, the third vector, rather than parallel to the tangent vector. We conclude that at least theoretically, the change in the frame has two different components. We can see this better if we view the TNB frame as points on a sphere. As we rotate around B, N moves towards T. It's moving in the T direction. On the other hand, if we rotate around T, we can see that N moves towards or away from B. It's moving in the B direction now. And of course, we can have more complicated motions. But in this one, notice that N is still in the TB plane. It just is a component in each of the two basis directions. Now we're going to think about something a little bit subtle. Does the acceleration frame have a twisting component? It's a good idea to do an example. Remember that we parametrized the helix, and we worked out its normal vector. It's not hard to take the derivative of these functions. And we knew the binormal vector as well. Now we need to go ahead and take the dot product of n prime and b. This is important enough that I'm going to pause the video for a few seconds and let you work out the answer to this on your own, either in your head or on a piece of paper. Ready to go on? That's good. So we see that the twist rate is actually 1/2, a constant that's not equal to 0. We're now going to watch the Frenay frame as the turtle traverses the helix. This takes a little bit of work to get your head around, so I'm running the video very slowly. The direction in which the turtle is pointing is the t direction. That's the tangent. The direction in which the turtle is accelerating is the n direction. That's the direction of the red ribbon. Also, the back of the turtle. The cross product of these two directions is the b direction. We see that at the right-hand side of the sphere. Now we notice, as n comes back, that it does indeed have a small but perceptible component in the b direction. I'll freeze the video right here so that you can see that n prime, the orange arrow, isn't pointing entirely along the meridian of the sphere that runs through t. It also has a component in the equatorial direction, which leads around the sphere to b. That component of the n prime vector is the twist rate of the Frenay frame for the helix. Now that component is honestly pretty small. So here's an example where you can really see the twisting in the Frenay frame. This curve is composed of arcs of circles, joined by almost imperceptible polynomial curves. When the turtle starts running, we'll see that it has to transition between the circular arcs, where the acceleration points towards the center of the circle, and the polynomial arcs, which somehow change between the two circles. You can see as it moves that it flips by 90 degrees as it passes through each junction. Here we see it together with its Frenay frame on the right-hand side. As we go through each junction, look for the n vector to suddenly get a large component in the b direction instead of turning solely in the t one. Here, here, and here. We'll slow the last transition way down so you can get a sense of what happens as we enter the turn. The vectors swing over, we turn, and then n returns to changing in the t direction as we complete the cycle. Let's watch this again while we take stock of where we are. So far, we've determined a frame by the acceleration of the turtle. That's certainly physically natural, but we found it twists. So the next natural question to ask is there a frame which doesn't twist at all? Let's think about what this frame would have to look like. Since the norm of the frame vector is always 1, it's perpendicular to its derivative v prime. That means that v prime is a scalar multiple of alpha prime plus a scalar multiple of alpha prime cross v. The first scalar, lambda, is the bending rate, and the second scalar, mu, is the twisting rate, and that's equal to 0. The other thing we know is that v dot alpha prime will always be 0. Let's differentiate this relation and see if we get anything useful. The derivative of that dot product is v prime dot alpha prime plus v dot alpha double prime. But we already know that v prime is lambda times alpha prime. So we know that lambda times alpha prime dot alpha prime is equal to v dot alpha double prime. Now we can solve for the unknown scalar multiple lambda s and get the following equation. V prime, which remember was lambda alpha prime, is minus v dot alpha double prime divided by alpha prime dot alpha prime multiplied by alpha prime. That is to say, v prime is some function of v and s, admittedly determined by alpha. This is an ordinary differential equation which defines the frame v of s. The solution to this differential equation is called a Bishop or inertial or sometimes a relatively parallel frame. We're now going to take a look at some inertial frames. Observe that when the turtle goes around this curve, it just turns as much as it needs to. There's no dramatic twist at the junctions. If we watch the frame as this happens, we see that the frame vectors are always changing in the direction of the tangent vector, but that they switch. Sometimes we rotate around F1 and sometimes around F2. Now we're going to look at the inertial frame for a helix as we expand the helix. You can see that unlike the Frenay frame, this frame is changing as the pitch angle changes. In fact, when we get to the end, you can see, interestingly, that this frame looks like it's twisting more than the Frenay frame, when in fact, it's twisting less. Watch the end of the frame as we change the pitch angle again. You'll see that it looks like the end vector is rotating slowly around the end of the helix. We can see the difference between the acceleration and the inertial frame more clearly if we plot them both together on the helix. Again, you see that while the acceleration frame always points in towards the axis, the inertial frame doesn't. Sometimes it points inward, and sometimes it points outwards. If we look at the inertial frame for the turtle moving around our original path, we can see that the turtle's motion is physically plausible. There's another secret of the relatively parallel frame, however. If you look at where the frame joins itself, where the yellow arc is, you can see that the frame doesn't quite close. The same thing is true if we take the inertial frame after 15 complete circles worth of rotation angle. It doesn't close. In differential geometry, we call this failure to close holonomy, and it's a topic that will come back later when we study surfaces.